Hello and welcome to the next installment of Introduction to Electric Circuits. This is a continuation of AC fundamentals. And in this particular lesson, we'll be looking at capacitance. So let's get started, shall we? Some of the things we'll look at today, we'll look at what is capacitance, and we'll look at some of the characteristics that make up or define capacitance. We'll then look and see how a capacitor reacts in an AC circuit, how it stores voltage or electric charge. This causes it to react to a changing voltage. We will then go through and do example problems on how to calculate current, reactive power, capacitive reactants in AC circuits. The simplest way to describe a capacitor is that it is two conductive plates, usually made of metal, separated by something. This something we call a dielectric. A dielectric is an insulating material, and something's dielectric strength refers to how much pressure or electrical pressure it can be put under and still insulate the electrons from flowing. A capacitor gets its name from the fact that it has the capacity to store electric charge. There are three main factors that determine the capacity of a capacitor. The first is the surface area of the plates. Capacitors store electric charge, and by having more plate area, you can store more charge. The second factor is the distance between the plates. Electric charge, or voltage, is the difference in charge between two places. The closer these two places are to each other, as in our case, the two plates, the closer they are, the more reaction will be between those plates, the greater the force of attraction. The farther the plates are away from each other, the less the force of attraction. The third main factor for determining capacitance is the type of dielectric material. Dielectric materials also help determine the voltage rating of the capacitor. Again, capacitors store charge. So the larger the surface area, the more charge we can store. The distance between the plates. The closer the plates are to each other, the more the charge will be attracted to each other, or the opposite charges. Just like we discussed back in Charles Dufay when we looked at the laws of charges back in DC. So the closer we can get the plates together, the greater the capacitance. The farther the plates are from each other, the less capacitance we will have. The type of dielectric also helps determine the amount of capacitance. A dielectric that has a higher insulating rating allows us to do a couple of things. It allows us to put more voltage on the capacitor, which is more charge, which means we have more capacity. And it also allows us to put the plates closer together, because the closer the plates are, the greater the force of attraction between the charges. The better the insulating rating, well, the closer we can put the plates together. So what goes on when a capacitor stores a charge? Let's take a look at that. Here we have two plates. Now in our example here, it's just separated by air so that we can see what's going on. Our two different conductive plates are separated by air, and they're connected to a 20-volt source. Again, if we go back to our definition of voltage, voltage is the difference in charge between two places. So our negative terminal, or the black terminal of our battery, has a whole bunch of negative ions. The positive plate of our battery has a whole bunch of positive ions. And our sources of EMF, through a chemical reaction, the electrolyte in the battery pulls electrons off of the positive plate, creating a bunch of positive ions, and deposits all the electrons onto the negative plate, giving us a large supply of electrons, or negative ions. When we hook a capacitor up to this difference in charge, the positive plate of the battery wants electrons. So what happens is an electron will come off of the metal plate of the capacitor. That'll force the one plate to become slightly positively charged. Since there's a difference of charge on our capacitor, where one plate is now slightly positively charged compared to the other, the second plate will then pull an electron out of the pile of electrons on our battery and place it on its plate in order to balance out the system. But we've only moved one electron. We've removed one from the positive plate, and we placed one on the negative plate. We still have a difference of charge on our battery. So our battery will again draw off an electron off of our plate of our capacitor, which will change the difference in charge, so that our negative plate will pull an electron off to try and balance the system. And this will keep happening over and over again, where it'll pull an electron off of the positive plate towards the battery to even that system out, which causes a difference in charge in our capacitor. And our capacitor will pull an electron out of our battery in order to try to balance the system. And it'll keep doing this over and over and over again until the voltage at the capacitor, or the difference in charge of the capacitor, will equal the voltage at the battery source, where both charges will be equal, but opposite of each other. Capacitors store electric charge, or coulombs. Current will flow while the capacitor is charging. It will also flow while the capacitor is discharging. The current will flow until the voltage of the capacitor matches the voltage of the voltage source. Current will continue to flow until the voltage of the capacitor matches the voltage of our source. We can remove the capacitor from the circuit once it's charged, and then use that voltage or charge to supply something. Current flows only when a capacitor is charging or discharging. The capacitor will remain charged even if we remove the battery from the circuit. If we provide a path, then the charge in the capacitor will flow through the circuit to rebalance the system. Capacitors cannot create voltage, but they can store it. And we can use that stored voltage to run something. A well-designed capacitor can remain charged for a very long time. Unless you provide a discharge path, the capacitor will only discharge itself through its dielectric material. How much current gets through depends on the quality of the dielectric material itself. We call this leakage current, where a few electrons will sneak through the dielectric insulator. This may take days or weeks for a capacitor to self-discharge. Here's an example of the electron orbits in an uncharged capacitor. It has no charge applied to it. The electrons, all being the same charge, will evenly distribute themselves around their orbits in their individual atoms. They are nice and uniform. When we place a voltage or a charge on our capacitor, the amount of voltage or difference in charge will impact the electron orbits. If we have a high enough voltage, what will happen is the negative charge of the electrons orbiting their atoms in the dielectric will start to distort or elongate. If there is enough charge difference or voltage placed on the capacitor, we can actually rip the electrons off of their atoms in the dielectric, at which point the dielectric will no longer be an insulator, it will become a conductor. This usually destroys the capacitor. The capacitor will then become a short circuit and will no longer be able to store a charge or function properly in the circuit. We call this dielectric stress. You must make sure not to exceed the voltage ratings of a capacitor, so that you not put it under undue dielectric stress, which will result in capacitor failure. Since capacitors store charge or voltage, they don't like any changes in the voltage. As we looked at earlier, a capacitor will store its voltage up in the opposite direction to the voltage that's applied to it. Capacitors store the opposite voltage. So capacitors don't like any changes in the voltage, and they'll react to any changing voltage. Much the same as our inductors oppose any changes in current due to the magnetic field, our capacitors oppose any changes in voltage due to the voltage field that is stored upon them. We call this opposition capacitive reactance, where the capacitor opposes any changes to the voltage. Since current is dependent upon voltage, then this also impacts our current according to Ohm's law. So we measure capacitive reactance in ohms. And we can calculate it by the formula where capacitive reactance, XC, is equal to 1 over 2 pi FC, where 2 pi is one sinusoidal period, F is our frequency in hertz, or how often our sine waves are coming at us, or how fast our voltage is changing, and C is our capacitance. We measure capacitance in farads. A farad is a large amount. So we usually measure capacitors in microfarads. Since our capacitors store voltage, and they charge up in the opposite direction to the applied voltage, when we have a continuing sinusoidal voltage, our capacitor is actually stored up to the voltage in the previous cycle. So that means as our voltage changes from negative to positive, as in the example here with our voltage sine wave, our capacitor is actually stored up from the previous cycle, which means we actually have a voltage source out in the circuit. This results in us actually having current out in the circuit. Because of this, we say that capacitance has a current that leads the voltage. In a sinusoidal system, it works out nicely that in a purely capacitive circuit, the current leads the voltage by 90 degrees. Now, if we were to look at our capacitive reactance, which is measured in ohms, and we use Ohm's law to look at it, where our supplied voltage is our reference, because that's what comes from our utility provider. We divide it by our current that leads by 90 degrees. Then we derive the fact that our capacitive reactance must be lagging by 90 degrees, or our capacitive reactance is at minus 90 degrees. So let's calculate out a capacitive reactance and a current. Here we have a 120 volt 60 hertz circuit with a 165.779 microfarad capacitor. When we put this into our capacitive reactance formula, we end up with approximately 16 ohms at minus 90 degrees. Don't forget to account for the prefix of micros, where a micro is 10 to the minus 6. Now that we have our capacitive reactance, or our opposition due to capacitance, we can calculate out our current. Again, just using Ohm's law principles, where current is equal to volts over ohms. And that results in 7.5 amps at a leading 90 degrees. Again, in a purely capacitive circuit, current leads by 90 degrees. Let's do another example to make sure that we have the mathematical operation down pat. So here we have a 240 volt circuit at 50 hertz, 63.66 microfarad capacitor, and that'll result in approximately 50 ohms at minus 90 degrees. Use Ohm's law to find our current, and that results in approximately 4.8 amps at 90 degrees. How'd you get along with that? Let's do one more. This time, let's have 300 volts, a 1 kilohertz frequency, and a little 2.5 microfarad capacitor. Since the frequency has gone way up, but our capacitance has gone down, we end up with 63.66 ohms at minus 90 degrees. When we calculate out our current, we end up with 4.71 amps at plus 90 degrees. So we've looked at capacitive reactance, where the capacitor reacts to a changing voltage, which impacts our current. How about power? Let's take a look at that, shall we? What does power look like in a capacitive circuit? So again, our capacitor. An electron gets pulled off of one plate to try and balance out the battery, which causes a difference in charge in our capacitor plates. So our second plate then pulls an electron off of the battery in order to try and balance out the system. And this process will keep happening until the voltage at the capacitor matches the voltage or charge of the battery. The negative electrons on our one plate are attracted to the positive ions of the other plate. And again, this charge will match our battery charge until Vc equals E. The electrons are attracted to the positive ions on the other plate. This creates an electrostatic field where the electrons want to get to the positive ions to balance out the system, but they can't because of the dielectric separating the plates. This creates a static field where there is the force of attraction, but it cannot flow. So now we have potential energy between these two plates. So we've stored an electrostatic field or potential energy on our capacitor. We call this capacitive reactive power. We use the symbol QC, again Q being reactive power, with a subscript of C for capacitance, and we measure this in volt-amps reactive. So it's very similar to what we did back in inductance. But instead of using L, we now use C. We can use any of our old Ohm's law power formulas with our new subscript in order to get to our values. So it's the same mathematical operation that we used to do before back in DC, but now with our capacitive reactive values. This makes the math a whole lot easier.
Hello and welcome back to the shop. Today we're going to be talking about capacitors and capacitance. It's going to be a short one with a quick demonstration about the static charge between capacitor plates. Now capacitors can take all kinds of different shapes. This big bad bank of capacitors here, this came out of a little wind turbine for part of the power factor correction, smoothing out the waves, taking care of all the harmonics and all that silliness. This little guy came out of a marker wave. It's part of the flyback capacitor. This one came out of an audio system. This one here, well, this is a filter capacitor that came out of a large power supply. Providing our juice today will be our Van de Graaff generator. Now, all the Van de Graaff generator does is it takes some electrons from down inside there, puts it on the rubber belt, and then deposits all the electrons on the big shiny globe at the top. So that's going to be providing our high voltage static source today. Now what I got going on is I got one lead coming out of here, and it's safely put on top of my risk assessment card pack, and then it's connected to the back side of this plate. The positive side of our terminal over here, this comes over and goes into this other plate. A simple capacitor is nothing more than two plates separated by an air gap or some sort of gap. Now, depending on the characteristics of that gap, it'll increase or decrease our capacitance. So let's take a closer look at this, shall we? So I'm going to turn on the generator. I'm going to get rid of my watch and anything else electronic out of my pockets. Then I'll turn this on. And nothing. There we go. Safety switch was off. As the static charge starts to build up in my Van der Graaf generator, you can slowly see the charge building up in my capacitor, which is simply two plates separated by some sort of insulator. In this case, the insulator is air. And as the charge builds up on one plate, the charge is actually building up on this one, the electrons here are attracted to the plate that is lacking charge there. And we can visually see that static charge, or that force of attraction, through our little silk strings. So as I move the plates closer to each other, you can see that there's a greater force of attraction because our strings are standing up straighter. As I move the plates away, there's less force of attraction, and they don't quite stand at attention as much. Here, I'll turn this guy a little bit more this way. So, one of the things that determines the amount of capacitance we have is the distance between the plates. The other thing that affects capacitance is plate area. So, the larger the plate area, the greater the capacitance. As you can sort of see here, you can see that the strings over here are much more attracted than the strings over here. You can also see where I'm sort of grounded that I impact the field. Now, if you're lucky enough to be of Germanic descent like I am, where we have significant amounts of body hair, you can actually feel that static field on your skin. And you can see the reaction of that field as I pass through it. The distance between the plates, the surface area of the plates, as well as the insulating material or the dielectric material between the plates, all impact the capacity of the capacitor to store voltage. Now, the cool part about capacitors, son of a diddly, is that if I turn this off, they will continue to store the charge. Now, depending on how good the capacitor is, it may maintain the charge for a very, very long time. Could be days even. That's why we usually put a discharge resistor into a capacitor bank network so that the capacitors will discharge themselves. Because this much capacitance can hold a lethal amount of charge. And that's the problem with capacitors, is they're sitting there, they can hold their charge for a long time, and that can be potentially fatal if it's a high enough voltage. To discharge a capacitor, all you have to do is give the electrons a place to discharge through. So there you have it, a real simple basic demonstration of capacitance, a basic capacitor, and in all its static glory. Capacitors store a voltage or electric charge. What else do you need to know? Yeah, how does it sort of work? Well, what happens is the generator is, in this case, is pulling electrons off of the first plate, this one, and then taking it through the system and depositing them on this plate. And that's what's giving us our difference in charge between those two plates. Again, by definition, a difference in charge is voltage, where 1 farad is equal to 1 coulomb stored at 1 volt potential. And there you have it. Until next time.
So what does that all look like? Let's take a look at our waveforms for our capacitive values. When we apply a voltage, it takes a couple cycles for the capacitor to get up and running fully. But once the capacitor is running, then the current will lead the voltage by 90 degrees. That means that as the voltage starts to go up, our current has to go down because our capacitor is discharging. Then our capacitor will start to charge up in the opposite direction according to the applied voltage. And this cycle repeats itself over and over again, where our capacitor is constantly charging and discharging. This results in a leading current. Now, if we were to take any of our power formulas, let's say volts times amps, to get our capacitive reactive power, QC, we would see that our power in our capacitor alternates at twice the frequency. Where, during the first pulse, where our current is positive and our voltage is positive, our capacitor is charging. Then, during the second pulse, our capacitor would be discharging or giving its energy back. And then that cycle would repeat itself, where during the third power pulse, our capacitor is charging up in the opposite direction. And then finally, during the fourth power pulse, our capacitor would be discharging or giving its energy back. Capacitors are constantly charging and discharging, where they're gaining power and then giving the power back. These power waveforms will become much more important once we look at both capacitance and inductance in the same circuit. So let's calculate some capacitive reactive power. But let's do that in a series circuit. What does capacitance look like in series? Well, we know that in a series circuit, ohms add, voltages add, current is common, and powers add. But what about capacitance? Well, putting capacitors in series is like increasing the distance between the plates, because one side of our source is attached to the left-hand plate of C1, where the other side of our source is attached to the right-hand side plate of C3. So now there's a huge gap between those two plates, the left-hand plate of C1 and the right-hand plate of C3. So putting capacitors in series is like increasing the distance between the plates. As we mentioned before, that causes our overall capacitance to go down. So when we have capacitors in series, our overall capacitance is diminished. And so it's a reciprocal sum for capacitance in series. When we go to calculate our capacitive reactance, which itself is an inverse function, then we get back to where all our ohms add directly. All of your old series Ohm's law principles still hold true. Where ohms add in series, voltages add in series, current is common in series, powers add in series. It's just capacitance is an inverse function in series. So let's take a look at these three capacitors in series. A 20, a 30, and a 60 microfarads. Capacitance in series is a reciprocal sum, and that will result in 10 microfarads for a total capacitance. Now we could calculate each of the ohms and add those up, because we know ohms add in series. But since we have our total capacitance, we can also calculate out our total capacitive reactance, which in this case works out to be 265.25 ohms. With our total opposition, we can now calculate our total current, which in this case works out to approximately 452.4 milliamps. Now let's take a look at our individual reactances, where XC1 should be about 132.626 ohms, X2 should be 88.41, and X3 will work out to be about 44.2-ish. If our Ohm's law formulas still hold true and principles for series hold true, then the sum of those should get us back to our XCT. And sure enough, they do. Now that we have our total current and our total ohms, we should be able to calculate each of our individual voltages. And again, voltages in series should add. And sure enough, when we add up each of the individual voltages, we do get back to our source voltage. As we carry on with our calculations, we've already calculated out our individual capacitive reactances. We got our total circuit reactance. We've got our total circuit current and our individual voltages. The only thing left to calculate now is our individual powers, our capacitive reactive powers for each of these three capacitors. We can go back and use some of our old Ohm's law formulas. We can use any of the ones we wish. I'm going to use volts times amps, which will result in each of the following capacitive reactive powers, which are measured in vars. Again, in series, powers should add, and that results in 54.288 vars. And again, it's always good practice to double check your answer, where our total power will equal our total voltage times our total current. And sure enough, within a margin of rounding, we get back to the same answer, as we should. How about capacitors in parallel? Well, as we add capacitance in parallel, it's like giving us more plate area to store more charge, which result in more capacitance, or more capacity to store charge. So when capacitors are connected in parallel, the overall capacitance increases. But once we convert our capacitance into ohms, then all our old Ohm's law rules for parallel circuits still hold true, where our ohmic values are a reciprocal of the reciprocal sum. So let's look at an example of a parallel capacitive circuit. We'll use the same values as we did before, just as we'll hook them up in parallel this time. Our total capacitance has changed. Our total capacitance is now 120 microfarads. which now results in a total circuit reactance of 24.1 ohms, which will then result in a current of 4.98 amps. Now, we'd already done the calculation on each of our individual reactances in the last problem, just as we've changed the configuration from series to parallel. Ohms in parallel, well, they add inversely. So if we take the reciprocal sum of each of the reactances, we get back to the total circuit reactance we calculated earlier. We know that currents add in parallel. So when we calculate out each of the individual branch currents and we add those up, we get back to our total circuit current. We could use our total circuit current by adding up the branch currents to get back again to our total capacitive reactive value. Since we've calculated all the ohmic values and all the currents for our circuit, and we know that voltage is common in a parallel circuit, well, now we can calculate out all the individual powers for each of these capacitors. Again, powers always add, and if we check it using ETIT, again we get back to the same as the sum of the individual powers. So let's recap, shall we? Capacitance is the measure of the ability to store electric charge. We measure that charge, or we measure capacitance, in farads. There are three main factors that determine capacitance. It's the area of the plates, where the more area we have, the more capacity we have. The distance between the plates, where the farther the plates are away from each other, the less capacity we have. Finally, the dielectric material between the plates will determine how much voltage and how much capacity we can put on those plates. Current only flows when a capacitor is charging or discharging. And since capacitors store electric charge, or voltage, they oppose any changes in voltage. Capacitive reactance is the opposition to current due to a changing voltage. We can calculate capacitive reactance by using our capacitive reactant formula. Capacitors have the ability to store energy in an electrostatic field. Our rules for series and parallel still hold true, but when it comes to capacitance in series, the capacitance is a reciprocal sum. And capacitance in parallel is a direct addition. This concludes our presentation on capacitance. In our next video, we'll be looking at resistance and capacitance in the same circuit. Thanks for watching. We'll see you next time.